All right, well, I'll get started here. So, what are differential equations, right? Anybody want to take a guess? What is a differential equation? Nobody? A differential equation is an equation which involves derivatives. This is profound, right? Mathematicians have really fancy ways of naming math, you know? And so, like, where are differential equations? Where do we encounter differential equations in science and engineering? And the answer is, well, pretty much anywhere one rate of change affects another rate of change, right? So where is that? Pretty much everywhere, right? Yeah, velocity, position, acceleration being famous examples. Physics 231 is a prereq, so we will do some physics in here. At no point will you be drawing a free body diagram, but you will be solving Newton's equations and solving for velocity as a function of time, stuff like that. We'll do all that. But I want to show a couple of examples of where differential equations naturally arise in the study of vector fields. So we'll talk a little bit about curves and vector fields. And this will give us a chance to review some basic concepts, like how can you talk about curves? Let me just get that right off the bat. There are two ways to talk about curves, right? We can either talk about them parametrically, or we can talk about them as like a Cartesian equation, right? Right. So parametrically, we describe a curve or a path like x of t and y of t, right? Something like t maps to, say, gamma of t, which is a pair x of t, y of t, right? Now, all of this t gets really annoying, so sometimes I'll just abbreviate this by saying something like gamma is equal to x comma y to say, hey, that's a path, and it has x component function x and y component function y. Now, Cartesian equation, generically, you might say something like, you know, you've got some function, let's say f of x comma y equals to, say, a constant. So that's a Cartesian equation. It's just involving x and y. There's no time, right? And so a special case of this would be something like, for example, y equals, say, little f of x, right? So you could say, like, f of x comma y is equal to, say, y minus f of x equals to 0. That kind of equation is called a what? What's this? This is what? Uh-oh. Surely someone here knows. Nobody? A what? A function, yeah. That's true. F is a function, but what is y equals f of x? The set of all x and y that solve that. It's a what? This is a graph, right? A graph of a function. So those are special. They have to satisfy the vertical line test, right? The solution set to an equation doesn't have to do that. It could be a circle, an ellipse, something that doesn't satisfy the vertical line test, right? Now, functions are kind of like like a graph is sort of, in almost sense, in a middle ground, because you could easily take a graph and write it parametrically, right? Like I could write gamma of t is, say, t comma f of t. This would be a parameterization of, you know, the graph. Where I'm using the parameter t, right? This should all be old news to you. You've had Calc 3, yeah? All right, just wanted to refresh your memory, the difference between parametric and Cartesian equations, all right? So, what's a vector field? So let me introduce something here. Definition. Given vector field, let's say big F equal to P comma Q, all right? We say gamma is an integral curve, or if you like, flow line of f if, here's how it goes, f of gamma of t is equal to d gamma dt. Now, that might leave you kind of like, what are you even talking about? Well, let me write this a little bit like more in terms of the p and the q. All right, so like in terms of p and q here, and if I so this means at gamma of t. All right, so like, so I could draw a picture for a second here. So here's my vector field. So here's like a picture of the vector field, let's say. So some flow lines to this might be something like or maybe, I don't know, there's someone in here, something like this. So they are such that at any particular point that you pick, like let's say right here, this, the vector field, so this point would be, for example, like gamma of t. So this, at that point, the tangent line, the tangent vector field rather to the curve, matches the vector field which is given. All right. So these are called flow lines or integral curves. Now, how do you actually find these integral curves for a given vector field? Well, let's break this down a little bit further. What does that actually look like? Well, this is as a vector. We've got p comma q, and how do you take what's the derivative of a path? Well, you've got the derivative of x comma y. We define that to be what? The derivative of x comma the derivative of y, right? So what does this mean? This means to find the integral curve to a vector field, we have to solve two differential equations. You see? What are the differential equations we have to solve? So apparently we need to solve p equals to dx dt and q equals to dy dt, right? The solution to that system of differential equations, they're first order, it's a first order differential equation. These are called ordinary differential equations because there's just one independent variable, which we're thinking of as time, right? So we can think of t as time. I suppose mathematically you can think of it as a parameter. But then the question is, how do you solve systems of equations like this? How do you solve a system of differential equations? Well, you guys had Calc 2, so you've solved some differential equations in that class, right? You looked at separation of variables, and you looked at the integrating factor technique. You should know those. We'll review them starting now. But like, here's an example. So example 1, let us take a look at the vector field f, which at x comma y is equal to x comma 2y. All right, let's find the integral curves of this. All right. So what do we have to solve? We need to solve, we're up against dx dt equals to x and dy dt equals to 2y. So we need to solve both of these at once. The good news is that this system of differential equations is really pretty simple. It's uncoupled. The x equation has to do with the x. The y equation has to do with y. We'll learn a technique called the eigenvector technique to deal with the case when they're intermingled in a week or a couple weeks. So, all right, so you solve these Calc 2 style, easy. So we got dx over x equals to dt. We've got ourselves a dy over y is equal to 2 dt. Separate, integrate. We get natural log the absolute value of x equals to t plus c1. Natural log the absolute value of y equals 2t plus c2. There we go. I think that wasn't bad, right? And I'd like to actually find the gamma, the parameterization of the integral curve here. And so I need to solve for x and y. So let's see here, I'll exponentiate both sides. That gives me absolute value of x is equal to e to the t plus c1. Absolute value of y is equal to e to the 2t plus c2. All right? Now these steps I'm going through right now are important. These will come up again and again and again and again and again. But I'm going to go through like all the details right here, right now, since we're all here. And all right, so what's next? Well, if you have absolute value of x, what that tells us is that if you'll forgive this, oh, wait a minute, it's not hideous, Carolina. It's gotten dark. Let's see here. So x is plus or minus e to the c1, e to the t, and y is equal to plus or minus e to the c2, e to the 2t by, properties of the exponential, laws of exponent. But I might as well just relabel the constant there something a little bit prettier, like, oh, I don't know, x naught. So I've got x is equal to x naught e to the t, and y is equal to y naught e to the 2t, which gives me, altogether here, the parametric curve, gamma of t is x naught e to the t, and then y naught e to the 2t. There you go. That, my friends, is a parameterization of the integral curve to this vector field. And where does it go? Like here, gamma of 0 is exactly x naught y naught, right? So like that's the, at t equals to 0, it's going through that point, and it should align with the vector field, right? Now there's one exceptional case here. Anytime you do separation of variables, there's something to watch out for. What does separation of variables invariably involve? Division by what? Well, division by something, right? And if that something is 0, what you did is nonsense, right? So this calculation fails when x equals to 0 or when y is equal to 0, right? So like, if x is equal to 0, how do you solve this? How do you solve dx dt if x is equal to 0? It's just 0. That's one possibility, but there are many others. What? X is a what? Dx dt equal to 0, the solution is x is a constant. It could be any constant, though. So like if dx dt equal to 0, x is a constant. In other words, it's a vertical line. On the other hand, if y is equal to 0, you have y equals to a constant. It's a horizontal line. Those cases, inadvertently, are nevertheless included in our general solution down here, which is a quirk of fate, but one will embrace. This often happens. In separation of variables, when you go through cases and you do calculations, sometimes an exceptional case that your calculation doesn't really hold for, nevertheless will be a solution which the differential equation allows for. That happened here. See, because, well, that's not quite true. I guess, my bad. I mean, I guess the other cases, I'm sorry, now I'm getting in the weeds here. The other two cases would be like gamma of t is x naught, y naught, e to the 2t, or gamma of t. I'm wrong. I should say this. These are the other two. These are the other two. This is annoying. These are the other two integral curves, either the vertical or horizontal lines. Those are the exceptional cases here. All right, so great. Now my question to you is this. So, great. I guess one question you might ask is why are you interested in flow lines? Do you guys know any reasons? Why are we interested in flow lines? Electromagnetic fields is a very good answer, yes, because in electromagnetism, the flow lines, we have to count the flow lines. That gives us the flux, and the number of field lines that then gives us, through Gauss's law, the charge enclosed, right? Or if you study fluid mechanics, the flow lines actually indicate the way the fluid goes, right? So if you dropped a little bit of dye in the liquid, that's where the dye would go. It would trace out the flow line, right? Flow lines are obviously an important way to understand the geometry of vector fields, right? A vector field is this infinite collection of vectors, one applied to each point, right? That's kind of hard to understand. Flow lines, well, that's kind of a little bit more of an accessible idea. So they're interesting to find. All right. Great. I hope I've sold you on flow lines. But how about this? What if I want to find the Cartesian equation of the integral curve here? How should I do it? That's my question. How should I find the Cartesian equation of this integral curve? So can you guys tell me? Let me put the problem out there sort of just formally. We've got x equals to x dot e to the t. We've got y is equal to y naught e to the 2t. We want to just find a description of this curve that doesn't involve time. What do we do? Solve for t. I like your t. I'm going to take your t and replace it with an e to the t, but I like that idea. So this is e to the t squared, right? E to the 2t is e to the t squared. But you're exactly right. We could solve for t. I'm just going to be lazier and solve for e to the t. So, I mean, we just got to find some place to meet in the middle, right? You're like, you're weird. Why would you do this? I don't know. But I did it. So it's like e to the t squared is really x over x naught squared, right? Which gives me y is equal to y naught times x over x naught, quantity squared. There you go. Hooray. That is the equation of the integral curve in this context. Yeah? So does this mean this is the way to find integral curves, like the equation of an integral curve? I don't think so. I don't think this is a good way, actually, because generally speaking, these parametric equations could be rather, well, ugly. So I'd like to show you another way to think about it in terms of, well, let's try to eliminate time. Oh man. I've got no juice. Sadness. All right. Well, hopefully there's still power in the shirt. We'll find out. This is kind of stale. It may or may not erase. I don't know. Okay. Whew. All right. Where'd the map go? Oh, it's still in there. I always refer to this as the map room because there's like some archaic map on the sidewall there. I need to make some measurements. I'm going to put up some whiteboard in here. I've been meaning to do it for years, but this year I'm going to do it. We're going to wrap the rest of this. Put one here. Put one in the corner. We're going to have one continuous whiteboard. That's what we're going to do.
That'd be so hard to transport. Just one gigantic board.
Oh, but you can buy whiteboard stuff at Home Depot for about $20 for an 8-foot by 4-foot sheet, and I have it too.
One single board.
Oh, one single board. They should have talked you out of that in like engineering economy or something, I would think. But I'm assuming you're an engineering major. Is it wrong? Okay. So there's a math major in here somewhere. Oh, 2. Are there more? 3. Is there another?
They're among us.
Yeah. It's fortunate for you engineers. If there were more of them, then we'd do proofs. No? What?
Oh, okay.
Oh, come on. Sadness. All right, so let's talk about integral curves, Cartesian. Derivation. There's a really neat trick to do here. So we're looking for, we've got f, I'll just recap here. We've got f as pq, we're trying to solve, we're trying to find what's dy dx, all right? Let's just get to that. So, you know, let's dy dx for an integral curve. So here's a sneaky trick, all right? So, well, dy dx should be dy dt divided by dx dt, right? So, I mean, I just divided by dt top and bottom, right? Yeah? Will the math majors agree? That would give me authority, right? Okay, I see a smile. That'll count. So we want dy dt to be what? For the integral curve, dy dt is supposed to be q, yeah? And dx dt is supposed to be what? It's supposed to be p. So if I can solve this differential equation, which has no time in it, right? Then that should also give me the integral curve. Let's see if it works for our example. So for example 1, what was my p and what was my q? So example 1, remix. There, I'll be your DJ today. There you go. Let's see here. So dy dx. You guys don't like DJs? Okay, well, I'll accept that. No, we're just like, we don't like you as a DJ. I'll also accept that. Let's see here. Where was I? Oh, yes, x comma 2y. So all right, so then what? Well, my q is this one in my current lingo, and this is my p, right? So I'm supposed to do 2y over x, right? Now, again, we find ourselves facing the kind of problem we learned how to solve in Calculus 2, right? And if you were brave, you could have solved this in Calc 1 at the end, right? Like, these have never been that hard to solve, have they? I don't think so. I mean, you separate the variables and you integrate. If you can do that, it's a separable problem. So in this context, we've got ourselves a dy over y is equal to 2dx over x. Integrate that thing. So this gives us natural log the absolute value of y is equal to 2 natural log the absolute value of x. And I'll add a constant on this side. When you're integrating an equation, we could add c1 and c2 to both sides, but we get just as much generality in our solution by just adding a constant on the right side or the left side. So I'll just add one constant. It is important that we add the constant we integrate. One common mistake students make in this class is just to tack on a constant to the solution as if that's something you can do. Well, that kind of depends on the structure of the problem. If you've got a bunch of algebra steps you've done between where you've integrated and where the solution is, you may be wrong, because the solution may not appear additively. The solution might have a constant which appears multiplicatively or division, or who knows what kind of fangled way it's going to work in. Like, look at this one here. If I exponentiate both sides, I get absolute value of y is equal to, oh, by the way, let me make a small step here. This is natural log the absolute value of x squared, yeah? So we've got e to the natural log the absolute value of x squared, and by laws of exponents, I have e to the c here. I'll do find plus c. All right, so that gives me y is equal to plus or minus e to the c times the absolute value of x squared. I could have simplified absolute value of x squared as soon as it first appeared. What is the absolute value of x? It's plus or minus x, right? What's the absolute value of x squared? Which is also known as simply x squared, right? So lo and behold, the solution has the form y is equal to some constant, I'll call it k this time, x squared. That is exactly what we found the other way, right? What's the difference, though? Well, the other way had a particular point that was on the curve built into the formula, right? So here I've just written the solution to the integral curve in terms of an arbitrary constant k. There's always these kinds of choices we have to make, yeah? Any questions? So let me kind of just like sort of take this discussion here and write a little theorem to find integral curves for f equals to p comma q. We may solve dy dx equal to q over p, which is also known as, let's see here, q dx minus p dy equals to 0. So I'm sure some of the questions I'll ask you in the homework, or perhaps possibly on a future quiz, or pretty sure it's in the team mission, is to find the integral curve to a vector field. And so this is how you do it. You just need to solve this little differential equation like so. Now, the equation I just boxed is maybe something new for us, yeah? This is an example of what's called a Pfaffian form. So Pfaff was a contemporary of Gauss. He did important work on the foundation and formulation of differential equations back in the 19th century. And so to write a differential equation in Pfaffian form simply means to not write it in terms of like dy dx, instead writing it in terms of differentials. All right? So writing a differential equation in terms of differentials can often be very, very informative. And well, let's talk about that. So any questions before I continue? So as you guys think back on vector fields, is there any particular kind of vector field which was of special importance in Calc 3? What kind of vector fields we talk a lot about? You remember? Remember conservative vector fields? Yeah? So we'd like to talk about conservative vector fields again and try to understand what those have to do with differential equations. I don't think I have quite enough time to finish that thought today, but I'll try to start it. So to understand conservative vector fields, really we need to understand from the perspective of so a couple things. Definition. F is conservative on U, a subset of Rn, if F is the gradient of some potential function F. So here this is the so-called potential function. Now in physics, we write something like F is equal to minus the gradient of, well, I tend to use phi in this context, where this is the potential energy. But I don't want to, I don't really care that much about energy in this course, usually. So we're just going to adopt Calc 3 and just not put the minus in because it's easier to think about without the minus. Yeah. So a potential function is a function whose gradient is the vector field, right? And conservative is something that depends on domain. So like a function could be conservative on like the punctured plane without being conservative on the whole plane. The punctured plane is the plane with the origin removed, all right? There are vector fields which are conservative on the punctured plane but not the whole plane. And this matters. So we've studied this in depth in like Calc 3. But anyway, that's a conservative vector field. Now, so I want to talk just more about like the geometry of potential functions. So if we have f of x comma y equals to a constant, right? This is usually called like an, well, this is a level curve, right? Of f. So a level curve of a potential function, you know, it's an equation, the solution set to an equation, a Cartesian equation. Now, in the case that that's voltage, this becomes like equipotential, right? So like an application of this would be like equal voltage lines for an electric field, which is conservative. But anyway, let's talk about the geometry here. So what if you had a parameterization of a level curve? What does that look like? What's a parameterization of the level curve? So if gamma of t is parameterization of, let me call this thing star, then f of gamma of t is equal to that constant, which I'm going to call c because I'm tired of writing constant, right? And that's true for all time that the parameterization is good for, right? So what we can do then is we can take the derivative of this equation with respect to time. And how does that work? What happens when you differentiate a function of several variables? So when you differentiate this, what we get is that the gradient of f at gamma of t dotted with the gamma dt is equal to the derivative with respect to t of the constant. But the derivative of a constant is simply 0, right? Yeah. And so what we're looking at is this equation. What this says is that the gradient of f is perpendicular to the tangent field of gamma. Right. And what does this mean? If I was to plot level curves, right? If this was a level curve, if this was a level curve, if this was a level curve, what would the gradient field look like to that? Yeah, I mean normal, right. So it's got to be exactly perpendicular wherever, you know, like that, yeah. I will regret trying to do this picture in 5 minutes. I mean, I started 5 minutes late, so I get to go 5 minutes over, right? The math major said it's okay. All right, maybe they didn't. Anyway, so you guys know how to draw perpendicular arrows. Okay, so what does this mean? This means that for a level curve, the gradient vector field does what? It points in the direction that you need to go in order to do what? In order to level up, right? So that's just a quick review of this math here. So what does this have to do with differential equations? Like, you know, what significance is there of conservative vector fields as it relates to first order differential equations? Well, we don't have quite enough time to talk about that today, but I'll talk about it next time. Let me tell you where we're going. So we're going to talk about how to solve first order differential equations. You've already seen the separation of variables technique enter into the discussion today, right? Past that, there are two other techniques. There is the integrating factor technique, which is a special technique for dealing with linear differential equations, which you should have seen in Calc 2, but we'll review it in total here, okay? And then the other method is called the method of exact equations. The method of exact equations has a deep connection with conservative vector fields, which we'll talk about. And I'll introduce a new tool to deal with that called differential forms next time, and something called the exterior derivative, which is something that you probably haven't seen before, but it's really simple, and it gives us a simple way of understanding exact differential equations. And then past that, there's a fourth bucket of things, which are the substitutions. There's a number of standard problems, like the Bernoulli problem or the Clairaut equation, where you can use a substitution, and by making a substitution, then you're able to convert it to one of the other three types. But that's pretty much it for first order problems, besides like numerical methods, visualizations, of which there are many, which we won't do much with. But anyway, that's pretty much it for today. Thanks, guys.